Welcome to the microwave communication course. Today we see another solid state device, that is gun diode, that we see today. So we know that earlier a tunnel diode. In a tunnel diode there is a tunneling action takes place, and in which there is a junction, and junction form between the P type material and the N type material. Now there are the two components there, that's about a P type and N type there. So in general that diode, it has a PN junction. But here in the gun diode, the junction is formed not using the P and N type. It is only either N type, or it is only either a P type here. So it doesn't have a junction. It is using only the single semiconductor material, either P type or a N type here. So most of the time we supposed to be consider that a P type and N type material, that is to be called as a diode. But here it is only a N type material, and the phenomena of transferring the electron based on the what will be the applied voltage. Now earlier case, if you see the diode, the electron transfer from the N to P here in a normal PN junction diode. But in the Gunn diode, the electron transfer from their low valley, or we can say that in a conduction band itself, but from the low valley to the upper valley here. And then because of that, so your diode will work in a negative resistance region. So means mobility of electron takes place here, and that is mobility of electron takes place in the given particular energy band. So we need to talk about that a electron transfer here. So that's why, so this gun diode is supposed to be called as a transferred electron device. It's just transferring the electron from lower region to the higher region there in a conduction band. So now, before start to understand that how this conduction band and a valence band is there, and how this electron transfer there, so we're supposed to learn first how this gun diode schematic is there. So gun diode, it has generally a high field domain inside the device, and basically a gun diode consists of a N-type gallium arsenide semiconductor material, and it has the electron concentration of around 10 to power 14 to the 10 to power 16 per centimeter cube. And these are the electron concentration at the room temperature. And generally, a typical dimension of this is about a 150 to 150 into 30 micrometer cube. And this one is about a gun diode here. We're supposed to see here. This one is about a gun diode here. And this, why this name of this diode is a gun here? Because JB Gunn found that a such N-type gallium arsenide semiconductor, that will provide a oscillations there, or through this, when we apply some certain voltage to the device, so then it produces some periodic fluctuation. Now what will be that certain voltage, or we can say that a threshold voltage there, and at that particular threshold voltage we'll get the current maximum. And then even if we further apply the bias voltage, even if we further apply the high field, then what happen, that current start decreasing, means all the electrons reach to the upper valley. So that's why there is no free electrons present in the device. So that's why current start to drop there. And then current start to drop. So in that case, your diode will work in a negative resistance region, and then this diode will be act as a oscillator here. Now we supposed to learn that what will be the velocity of that particular carrier. Generally, we supposed to say that initial condition there is no bias. Okay, so then velocity electrons are at as it is in the given particular band, and then when we apply some certain bias there, the electrons start to move there. Means it has some velocity, and that velocity of the electron generally we say it is about a drift velocity there. Means whatever the okay we say a carrier move from this region to the another region, so it has some velocity, and that velocity if supposed to be you take with respect to how much is the bias apply. So according to that, this drift velocity will decreases after certain threshold value there. Now the phenomena of this Gunn diode work in a given particular applied voltage. In that case, we supposed to be consider at some particular voltage it work. That effect is called as a Gunn effect here. So to understand the Gunn effect, we are supposed to say that a Rayleigh Watkins held some theory there. So that's why we say that the RWH theory, and that RWH theory is based on the transfer of electrons from a one band to the another band. So which one is that one band? So we'll see that. Okay, now generally here it has a cathode, a anode, and this here a high field domain here. Okay, in generally we say that high field domain, and that high field domain is formed at a cathode, and then high field domain start to move from the cathode toward the anode, and then at this particular anode it dissolves. So before dissolving this particular high field domain, so again another high field domain will start at the cathode. Okay, so means it will move. The domain will move from the cathode to the anode, and then it will be dissolved at this particular cathode. So we talk about this high field domain later. First of all, we understand that how electron we can say that how electron will be transferred from one band to the another band. So that's why we supposed to consider that a if that we can say that a band diagram. Okay, so for a given particular Gunn diode, so what will be the a band diagram there? And for this, we supposed to use a two valley model for the electron with respect to their energies there. So now we supposed to consider that this one we supposed to say that this one is about a conduction band now. Okay, then in between that a valence band. So this one is about a forbidden band, and then this one is about your valence band. Then in a conduction band, there is the lower valley. Okay, we have the lower valley here, so in which there will be the mobility of electron and the mass is different here. Okay, so generally we say that a mobility it will be higher in the lower valley. Okay, then another valley that is called as a upper valley. This one is about a okay. This one is about a upper valley. Now here we say that this one is about a RWS theory. So it means we can say that transfer of a conduction electron from a low mass, high mobility band to the high mass, no low mobility band. So this one is about what we can say that a low mass. This one is about a band we say that it has a low mass here. Okay, this one is about a low mass, and it has a high mobility. Okay, mobility is higher here. And this one upper valley here, it has a high mass. Okay, this one is about a high mass, and in this upper valley, we're supposed to consider that a low mobility. Okay, this is about what we said, that a upper valley. Okay, so now here the energy level, if you see that, so we have the a valence band, then a forbidden band here. So in between the forbidden band, we're supposed to consider that a energy, or we can say that a gap voltage, that is about a 1.43 EVM. Okay, so now what happened here? So this one here we have the high mobility electrons in this conduction band here, and there will be a low mobility electron in this band. But generally, if you consider that, so there are the electrons in the given band. Okay, most of the electrons are present in this given band. Okay, that is about a lower band. When we apply the bias, when we apply a field to the this device, then what happens? So then electron will try to move from this lower valley to the upper valley. Okay, so when we apply sufficient bias, then what happen here? So electron in this lower valley will jump from this lower valley to the higher valley there. Okay, when we apply the a bias there. So means what we can say, that here we have the higher mobility here. Okay, that electron is having the higher mobility here. When we apply the bias, that they will jump from the high mobility to the low mobility region. So that's why we can say that electron from the lower valley to the upper valley, when it jumps from the lower valley to the upper valley here, so their mobility decreases. Okay, their mobility decreases, and then naturally that current decreases here. Okay, so that is about what we can say here. We supposed to be consider that a graph here. So when we apply, supposed to be some certain a field now. Okay, or we supposed to certain a bias here, suppose. Okay, so in that case, we supposed to be apply a electric field, and this one is about what we say, that a drift velocity. Okay, even we can consider in terms of a drift velocity. Now what happened here, when we apply some certain value of a field here, so in that case, velocity, because the mobility is large, so drift velocity is large here, and then at some particular threshold value, at some particular threshold value, that is about EH here. Okay, and then the drift velocity, because we can say that a mobility decreases, because it will move in a certain region there. So this way we supposed to consider that this is about a EV here, this is about a EU. Okay, and this was about a applied some particular value, that's why some particular threshold value. So this one is about a drift velocity. So this one is about a diode will work in a negative resistance region. Now in general, if you consider that any type of a diode, okay, any type of a material, so this occur, this about a, it has a valence band, so forbidden band, and a conduction band. Okay, we supposed to consider that. So we have this a valence band, okay, forbidden band and conduction band. The same band is there in the normal semiconductor material, but it has only a one certain layer. It doesn't have a two layer, that is lower valley and upper valley, in a normal semiconductor diode. Okay, in normal semiconductor material, but only in a gallium arsenide material. So it has a two different valleys in a conduction band. Okay, and these valleys have a high mobility and a lower mobility. But okay, so electron to be jump from this or pass from this lower valley to the higher valley. Okay, so when this electron will pass, when we apply up certain field to the device, then and then it will pass from this lower valley to the upper valley. So in that case, when we say that electron passing from this lower valley to the upper valley, so then a current start increases. Okay, if you consider instead of drift velocity, if we consider that, okay, we supposed to be consider that instead of a drift velocity, we supposed to consider that whatever the bias we apply, that is about a DC voltage we apply, and we supposed to be consider that there is a current now. Okay, we supposed to be consider there is a current. So in that case, what happened that electron that move from this lower valley to the upper valley. Okay, so means what? From the lower energy state to the higher energy state. Electron move from the lower energy from to the higher energy state. So in that case, so what happened here? When it starts moving from this, electrons moving means what? A current start moving. Okay, okay. Sorry, current increases here. Electrons mobility increases by applying the voltage there. So mobility of electrons start from the lower valley to the higher valley here. So it gains some particular drift velocity. So that's why current start move increasing. Now current start increasing at some particular certain value of a threshold value of voltage. Okay, at some threshold value. So this one is about some particular a threshold value. We're supposed to say that VTH now. At some certain threshold value, it start increases there. Means at some threshold value, all the electrons from the lower valley, all the electrons from the lower valley to the upper valley will jump. Okay, it will jump from the lower valley to the upper valley. So at that some certain value, so this valley doesn't have electrons, mobility electrons. Okay, electrons are not present in the valley. Then there is no electrons present in the lower valley. So that's why current will not increases there. Okay, so there is no current. So that's why a current, even if we apply some particular further bias, then current start decreases there. Okay, this is about certain threshold value. So current start decreases and then it will be increases here. So here electron from when we apply some certain voltage, okay, this one particular voltage. So we say that initially current increases at some particular value, okay, of that's current. Okay, this is called as a threshold current, or this one is about a threshold maximum current. Here, okay. Okay, this one is about a maximum current. That maximum current occurs at some threshold value. So means all the electrons will transfer from the lower valley to the upper valley, and then there is no electron present. So that's why the current start decreases. Okay, that's why the current start decreases. And this particular region we're supposed to call, we'll get the value here. And this particular region is called as a negative resistance region. Your diode will work in a negative resistance region. Okay, this Gunn diode will work in a negative resistance region. Okay. So now we say that here maximum current reach at some particular threshold value and then it start decreases here. So that's why this one is called as a negative resistance region there. So your diode, what we can say that in a negative resistance, already that electrons are moving from this lower band to the higher band there, and when it starts from the moving from the lower band to the higher band, so electron will be immobile. Okay, so electrons are immobile. So here the higher mobility, here is the lower. So that's why the electrons are immobile. So that's why the current start decreases. Okay, now this one is about a theory. That is about a RWH theory here. Okay, that is about what we can say that Ridley-Watkins-Husserl theory. Okay, this one is about you. We say that a RWH theory. I'll write here. This one is called as a RWH theory. And that RWH theory will tell you what will be the mobility of electrons takes place inside the gun diode. And that's why this is called as a gun effect. Okay, what we can say that eh, after because of some certain voltage we apply or some field we supposed to say that when we apply some certain field, so then your gun diode will exhibit in a negative resonance region. Okay, so then this is about what we say a gun effect. So we supposed to find out that what will be the densities of the electrons in the lower values and the upper value. What is the density of the electron? And then we supposed to find out that from this for a given gun diode, this one is about a gun diode is nothing but what? A N type gallium arsenide. For this N type gallium arsenide gun diode, so what will be the conductivity? Okay, in the N type gallium arsenide, the conductivity is depending upon that what will be the electron densities in the lower values and the upper values there. So we can find out that a conductivity based on that a their electron density. So now we write here, okay, we write here that a conductivity is nothing but what? Whatever the charge we supposed to consider that, and what will be the electron density, and this is about electron density, and this one is nothing but the mobility in the lower value, and what will be the electron density in upper valley and a mobility in a upper valley. So from this we'll get the a conductivity here. And we say that a conductor exhibit that this semiconductor diode or this device exhibit in a negative resonance region because we say that electrons in the lower valley, okay, they should have a lower effective mass and a higher mobility. Okay, electrons in the lower valley, they should have the lower mass and higher mobility, and then they they will propagate from this lower valley to the upper valley. Okay, so whatever the separation of this lower valley have the lower effective mass and high mobility, and upper valley have a high effective mass. Okay, that mass is high here. Okay, high effective mass and the lower mobility. And the energy gap between this lower valley and the upper valley must be less than the band gap energy. This one, Eg. We supposed to consider that a band gap energy that is about a Eg. Then and then it will work in a negative resonance. If supposed to be that energy is not more than this band gap of energy, then what happen? Electrons in the lower valley begin to jump from this lower valley to the upper valley there, but the valence electron will jump from to the lower valley. What is the valence band here? So this one, here is the conduction band. We have a forbidden band, and this one is about a valence band. Valence band is it has some particular electron. If supposed to be this energy, we supposed to say that sorry, this one we supposed to draw here a forbidden gam. This one is about a conduction band. This one is about a forbidden gam band here. Okay, and this one is about a valence band. Now this one it has electrons in the valence. Okay, electrons in the valence band. So now this one is about a gap energy. So this energy and this energy. Okay. this energy from the lower band to the upper band. So lower energy, lower band to the upper band. Now this energy gap between the lower valleys and upper valleys, it should be much less than this a forbidden gap. Okay, so that what you can say that this one is about it, whatever the gap energy from the lower valley to the upper valley. This energy is to be less than this energy. If this energy is higher, then what happens? Based on the sufficient electron, then electron from this valence band will move to the lower band. Okay, electron from the what we can say that valence band to move to the lower band. So that's why after this we supposed to consider that a negative resistance region, all the then electron from this particular band is to be propagating. Even if we supposed to be consider that, so due to the a thermal effect, okay, that electron from the lower valley to the upper valley, they can jump from the lower valley to the upper valley. Okay, so that can be possible there. So that's why we supposed to know that what will be the thermal effect occur on this a gun device or a gun diode, and then we're supposed to consider that how much is the bias voltage is to be applied to this a device. And normally we say that this diode will work in a negative resistance region, and generally we say that this device will work in a two different mode. One is about, we say that, a voltage control mode, and another is about a current control mode. Okay, so I'll draw here, I'll write here. Okay, there are the two modes there. One is about a voltage control mode and the a current control mode. So now if consider that this voltage control mode and a current control mode, these are the modes, they are separate the two different fields. Okay, two different field domains. Okay, so that's why we can say that a voltage control mode and a current control mode. So in this case here, as we have seen that a high field domain there, high field domain formation takes place. Now we're supposed to consider that how this high field domain and a high current there. Okay, so just like we supposed to consider that we have the field here, so that's why it's called as we can say that a voltage control mode. And in a current control mode, we have the high current density in the given filament there. So that's why we have the high current. So we're supposed to say that this one is about a diode, and for this diode, it has supposed to be a high field now. This one is about a high field domain. Okay, and from this, we're supposed to find out the this one. These two regions are nothing but a low field one. Only at some certain point, this particular domain is formed, and that domain is called as a high field domain. So how this domain formation takes place? Okay, we'll see that. Now, when we apply the current, okay, this domain will move from one end to the another end. Okay, so similarly, in a current control mode here, so we'll see that what happened in a current control mode. We're supposed to apply current here. We're supposed to see that one is about a domain, and that domain is because of that a current. So that's why we can say that a high current. This one is about a high current, and this one is about a field, high field. This, and this one is all other are nothing but a low current here. That domain form here, okay, in this diode here, that domains are formed. One is about a high field domain, and that high field domain separates the two low field domain. These are the two low field domain here, and that happen in a voltage control. That happen in the voltage control, and in a current control mode, high density current filament. Okay, it is formed here. This is about high density current filament is formed, and that separating this low current density. Okay, this one is about a low current density, high current density and low current. And this field domain, it will be run along with the field direction. It will be run along with the field direction. So here a voltage current domain. Now how these are the how this will work here. So in general, we supposed to consider that a density and we supposed to consider some field we apply. So in a voltage control mode here, so it will the graph it will reach at the peak here, then start decreases and then it will act likewise. In the case of a current, okay, in the case of a current control mode here, so we have the density here. So at some certain value of a field, okay, when we supposed to consider a field increases there, start decreases, then it will work. This one is about a voltage control mode, and this one is about a current control mode. So, okay, so in which we supposed to say that a negative resistance region in the voltage control mode and a current control mode. Now, how this domain form here? Okay, so we supposed to consider that a domain formation is takes place. Okay, in that case, what we can say that when we apply some certain bias there, they, in that case, all the electrons are accumulated at some particular point here. Okay, all the electrons to be accumulated at some particular point here, and through that a domain formation is takes place. So generally, we supposed to be consider that for a given particular diode. Okay, so here the domain formation will be takes place here, and that domain is nothing but a small region or small teeny region there, and this domain is formed because of we apply the field to the device, and this domain has the higher intensity as compared to the whatever the field we apply here, and that particular domain formed in a given region. Okay, supposed to be consider that this one is about a device. Suppose we supposed to be consider here is a domain form, and now in this particular domain, this domain formation takes place here. So here it has a higher intensity at this particular domain, and these are about the lower intensity in terms of it. So this one, this domain will travel from what one region to the another region. So the domain generally domain is not formed at the center of the device here. It is to be formed. The domain is to be formed from the when we apply some certain bias to this given particular device. So generally we supposed to consider that this one is about a cathode. Now this one is supposed to be considered. This one is about a cathode end, and this one is supposed to be a anode end. Okay, now this one is about your anode. Or I'll draw here. I'll write here instead of that. This one is about we say the anode end now, and this one is about your cathode. So right here. Okay, now this one is about a cathode. Now what happened here? Here, when you apply some certain bias, okay, when we apply some certain bias, so here we supposed to that even this field will be created in this region here. Okay, across this cathode. So this one is about a high field domain. Okay, this high field domain it has a highest intensity there, and we have the electrons are there. That electrons are slow in this particular domain. When you apply further bias, then electron will move faster, and then because of that moving this electron there, when you apply the bias, then the domain will move here. Okay, how we supposed to consider that your domain will move here. Okay, so we supposed to be consider that at a certain value here, so this will move. Okay, so how it will move? So from this region, I supposed to be consider that here instead of this one, so it will be move in this given region. Okay, Then after again certain voltage we apply, then domain will likewise. And at the end, the domain will reach to the another end. Okay, that is about the anode. Then when it will reach to the anode here, okay, this particular region, then again another domain will start from the cathode. Okay, so that this way we can say that a domain formation will be takes place in the Gunn diode. And generally we say that domain will domain start to generate when we apply some certain bias, and then when we apply further uh, field to the diode device, then domain starts moving. Means what? Electron will move faster there. Means the domain start moving means what? Electron will move faster there, and then it will reach to the certain particular region. We supposed to say that if supposed to be anode and cathode is there, so I say that now this one is about a cathode and this one is about a anode. Now. So here it will start moving from this, electron will start moving from this to this here, this region. Okay, so this way domain, say now this one is the domain now. So now when we apply the bias, then domain start moving toward the anode. When it reaches to the anode, then another domain form. Okay, then it will go out. Then it will start here, then another domain. Okay, like it will move, then it will start. So likewise. So this way your domain formation will be it expressive. And then domain will not be disappear when it reaches to the anode, but another, because we supposed to apply some bias, so that's why again a domain will start here. Okay, so this way that when this domain formation takes place at some particular threshold value of a voltage. So another domain we supposed to say that a dipole domain. Okay, so that means your device will work, okay, in the given particular domain, and that domain formation takes place in the given device. So that's called as a formation of electron dipole here. So that's why we say that this one is about a minus minus here, this one is about a plus plus here. Okay, this one is about a formation of a electron dipole here. Generally, we say that a domain starts from when we apply the electric field at some particular point, and then the domain formation will be takes place, and because of that, we can say that at that domain will drift through the device. Okay, domain will drift through the device there. And this one is about, we say that a formation of a electron dipole here in a domain there. Okay, this one is about minus and plus. That's why we're supposed to say that a dipole domain there. Then there are the various modes of operation, and that modes of operation, based on that, how much will be the mobility and what will be the, we can say that what will be the length there. So generally we supposed to be considered for a given particular device that whatever the gun mode or modes of operation, that is depending upon that the operating condition of the device. So there are the one various modes. Out of that we supposed to consider that first mode is about a Gunn oscillator mode. Okay, means your diode will be act as a oscillator. Your Gunn diode, this one will be act as a oscillator. And this mode is generally defined in terms of what will be the a frequency and what will be the length there. That's why we're supposed to say that F and L here. And how much will be the a dopant concentration there. So that dopant concentration generally we're supposed to consider that supposed to be frequency here, and this one is about the length, and we're supposed to consider that a doping concentration and what will be the length there. If the doping concentration is greater, then we're supposed to consider that in the given particular doping concentration, then this device will work as a Gunn oscillator mode. So generally we supposed to consider that a N-type diode, N-type gallium arsenide sample, so that will be work as a Gunn oscillator when that concentration will be become say 10 to the power 12 per centimeter square. Okay, so means what we can say that this N0L, okay, in a gallium arsenide, this N0L, if it is greater than this 12%, then what happened there? So then this at this particular sample it will work as a Gunn oscillator. If it is greater than that, then in this case the perturbation occur in this device. And for this a Gunn oscillator mode, we supposed to calculate the frequency is about what will be the domain velocity there and what will be the effective length. That is about the effective length. Supposed to write here. This one is about the effective length. And this effective length, generally we supposed to consider that effective length, that domain travels from the where we say that this one is about a, we supposed to consider that domain. Okay, so likewise. So in that case, this one is about the effective length. The effective length means what? That effective length, the domain travel from that particular time at the start formatting the domain here, and this one we say that domain form here, then it will move here further, and then it will reach here. Then another domain start. Okay, before releasing here, so another domain form. So this one, here is the domain formation start here, then domain move here, then another domain start. So that this one is about a time, and that's why that is about the effective length. The domain travel from the time of a formation until the generation of the a new domain there. And that domain depending upon the drift velocity, and the drift velocity it is a function of the what will be the field we apply, so that your gun oscillation gun your gun device will act as a oscillator there. And then gun oscillation occurs, whatever the gun oscillation we supposed to consider that it occurs in a three possible domain mode. So one domain mode is about what we can say a gun oscillation mode we supposed to consider now. So in which we supposed to consider that a three different mode. One is about a transit time mode, transit time domain mode. Then another is about a delayed domain mode. Okay, and this one is about A, B, and C. That is about a sequenced domain mode. Now these are the three domains here. So we will see that one by one. That is about a transit time domain mode, then a delayed domain mode, and a sequenced domain. Okay. So now in a transit time domain mode, what happened here? F0 into L is approximately equal to 10 to the power 7 centimeter per second here. And in that case, PD, we supposed to consider that domain velocity is about a 10 to the power centimeter per second. And the oscillation period that is equal to the a transit time period. That is about T0 is equal to tau here. And we supposed to find out that how this domain arrive at this particular anode, and that's why according to that we're supposed to say that efficiency of this a device there. So here we consider this one is about a voltage V here, so about a T time period T here, and then this one is about a DC bias. Then this one is about a ETH here. Then we supposed to consider that yes here. Now we say that we have the DC bias, then domain grows here, and then it will reach below this threshold value. Okay, it will reach the below threshold value. So now this one is about a what we can say that is about a tau. That is about a T0 is equal to a tau here. And this one is about a negative resistance region. We're supposed to say that negative resistance region. And then further it will be increases here. And this supposed to be considered as a positive resistance region. And this one is about a negative resistance region. So this one is about in this case here, a domain collapse in the positive resistance region and domain rose in the negative resistance region. Okay. So that is about what we can say that a transit time domain. Okay. So we stop here